One, in the last video, we have seen phase shifters and terminations which are used in the microwave circuits. In this video, we will see another type of device which is passive device which is used in the microwave circuits. They are called as attenuators. Okay, so what are the attenuators? Attenuators are passive devices used for reducing power levels to the desired levels. Okay, we know power can be amplified by using power amplifiers. Now to reduce the power levels we can use attenuators. Okay, so amplification can be done by amplifier. So how does the attenuation is done? So for attenuation, the power levels are absorbed by certain material. So attenuators control power levels in microwave system by partially absorbing the transmitted microwave signal. So there are several types of attenuators. We will see some of them. Fixed and variable are the two basic types of resistive card attenuators. Resistive card attenuators means resistive card or resistive pad is used for producing the attenuation. So resistive films or which is consisting of a dielectric glass slab coated with the aquadag. Aquadag is a material which is used for constructing the glasses. It is used as a dielectric material. It is tapered and inserted into the waveguides or other passive devices to produce the attenuation. So on your screen you can see two diagrams. First one is a fixed version or fixed attenuator where dielectric slab is fixed inside the waveguide, rectangular waveguide, and the second one is a variable version where dielectric slab is allowed to go inside through a non-radiating slot. So if you keep it out of the slot, then there will be no attenuation. As you move the resistance card or resistive card inside the waveguide, attenuation will be produced. So let's see different types of fixed and variable attenuators one by one. Apart from rectangular waveguide, other passive devices can also use attenuators. So such one of them is coaxial fixed attenuator. As the name suggests, it is a fixed attenuator which is used for coaxial lines. So it uses a dielectric lossy material inside the center conductor of the coaxial cable or coaxial line to absorb some of the center conductor power propagating through it. So as you can see in the diagram, this is the center conductor. When a wave is allowed to pass through it, inside the center conductor, lossy dielectric material is inserted, which absorbs the power and allows some power to go through it at the other end. The dielectric rod decides the amount of attenuation introduced. So the length of dielectric rod, the size, and the type of material used for making that dielectric rod will decide the amount of attenuation introduced. So the microwave power absorbed by the lossy material is dissipated as heat. As power is also one form of energy, so as we all know, energy cannot be destroyed. That means you have to convert it into some another form. So the power which is inside a microwave signal must be converted into some other form, and that other form for this type of material is a heat. So the power, if it is, let's say, P incident, some part of this P incident will be absorbed as a heat, and P transmitted, which will be less than P incident, because some power is absorbed by the dielectric rod as a heat. Okay, so that is how dielectric rod can be used in a coaxial cable to produce attenuation. Then for movable when or fixed or variable attenuators, first type is movable when attenuator. Now as the name suggests, the dielectric material is movable inside these type of attenuators. Let's see how it is done. In waveguides, a dielectric slab coated with aquadag is placed at the center of the waveguide parallel to the maximum E field of the dominant TE10 mode. So for TE10 mode, if electric field is in this direction, that is, let's say y direction, y axis direction, then dielectric slab is placed at the center of a waveguide parallel to the E field direction. That means it will be placed like this one. So both are in the same direction. If dielectric slab is placed like this one, that means on the horizontal direction, in the x direction, then it will be a perpendicular. Since it should be a parallel, the height of the dielectric slab should be in the y direction. Okay, so that is the meaning of that first statement. So the induced current on the lossy material due to incoming microwave signal results in a power dissipation leading to the attenuation. Similar to the coaxial line, the current induced in the lossy material will lead to the attenuation because there will be a power absorption in the dielectric slab. Now we have seen this slab is tapered along the both ends. That tapering is done for more than half wavelength length to reduce the reflections. In case of phase shifter also we have seen this concept. If we use dielectric slab simple like this one, there will be reflections along this dielectric slab. So to avoid them, it is tapered to a certain extent and made like this to avoid reflections. The dielectric slab may be made movable along the breadth of a waveguide by supporting it with the two dielectric rods separated by a odd multiple of quarter guide wavelength and perpendicular to electric field. It's a very long statement, so let's see what it means. Dielectric slab is made movable along the breadth of a waveguide. So on your screen you can see movable Venn attenuator. In the figure A, the 3D version of that movable Venn attenuator is shown, and in the B, front view of movable Venn attenuator is shown. So this is the front view and this is a 3D view. Now this is breadth of the waveguide. Okay, so how it is placed? This is the direction of electric field. So this will be a y direction, this is z direction, and this is x direction. Okay, now the dielectric slab is placed inside the waveguide along the parallel to the electric field of a TE10 mode, as you can see, and it can be made movable by connecting two rods. Here two dielectric rods are shown which are separated by quarter wave wavelength. Okay, quarter guide wavelength. So the difference between these two rods, okay, let's avoid confusion. So difference of length between these two rods is multiple of guided wavelength divided by 4. Okay, so length is lambda g by 4 between the two rods. Now these rods help moving the dielectric card or dielectric slab in this direction or in this direction. So forward and backward. Depending on where you are placing the dielectric slab, the attenuation will be made, or amount of attenuation will be made. Now in the front view you can see this is at the center. Now at center it produces maximum attenuation. The reason is that in TE10 mode, maximum electric field is at the center of the waveguide, and when dielectric slab is placed exactly at the center of a waveguide, then the maximum attenuation will be observed. As you move along the walls or towards the walls, then attenuation will be increased or decreased. Okay, decreased, not increased, because this is the maximum one. So if you move here or here, the dielectric slab, if it is moved here or here, then the attenuation will be decreased. Okay, so this is how movable Venn attenuator works. When the slab is at a center, attenuation is maximum because electric field intensity is concentrated at center of TE10 mode, and when it is moved towards the side of the walls, attenuation goes on decreasing, thereby controlling microwave power coming out of the output port or other port. Okay, so this is second type of attenuator that we have seen. Then there is another attenuator which is a variable attenuator. It is called as a flap attenuator. This type we have seen in the initial diagram. A flap attenuator is also a variable attenuator, as can be seen from the diagram. A rectangular waveguide is attached a flap which is made up of lossy dielectric. So this is a flap. This is a flap which is made up of lossy dielectric, and it is made to descend into the longitudinal slot cut. This is a slot which is non-radiating slot cut at the center of a top wall. So center means this distance and this distance should be equal of the rectangular waveguide. So this flap will move inside this particular slot and go into the waveguide. When this flap is completely outside, attenuation is 0. And when this flap is completely inside, attenuation will be maximum. So how much attenuation you will want, that is dependent on, or how much attenuation you will get, that is dependent on how much the flap is inserted inside the waveguide. Okay, so let's see. When the flap is completely outside the slot, attenuation is 0, and when it is completely inside, attenuation is maximum. So it is observed that maximum of 90 dB attenuation is possible with this type of attenuator with VSWR, that is voltage standing wave ratio of 1.05, so which is very good. The dielectric slab can be properly shaped according to the convenience to get linear variation of attenuation within the depth of insertion. So in this diagram it is shown that it is semicircular, but the amount of this flap is inserted, readings can be taken if it is showing different curves like exponential, like this one or this one, for different amount of insertion. Then you can make this curve linear one. So that means the amount of insertion will show linear curve if its geometry is changed. For example, like this one. So flap can be made like this one, it can be made like this one, like anything. So depending on how much variation you want in the attenuation, you can change the geometry of the flap also. Okay, so that is a flap attenuator. Then another variable attenuator is a precision type variable attenuator. Now interestingly, we have seen this type of device already in the phase shifter, that is precision type rotary phase shifter. Now the construction is similar. If you remember, this consists of a rectangular to circular transition. We are abbreviating it as a RCT. So first is a rectangular to circular transition, then followed by a circular waveguide, then again followed by a circular to rectangular transition. We will see the diagram. So there are three types of waveguides in this type of attenuator: RCT, CW and CRT. Now resistive cards RA, RB and RC are placed inside these three sections as shown in the figure. So let's see the figure. We have seen this diagram already. So this is RCT, rectangular to circular transition. This is CW, that is circular waveguide, and this is CRT, that is circular to rectangular transition. Then inside this three resistive cards RA, RB and RC are placed similar to what we have done in the phase shifters. Now what is the difference between this one and phase shifter? The placement of these resistive cards is the difference between the phase shifter and attenuator. Although the device is same, the cards are placed differently in the attenuator compared to the phase shifter. Now attenuation should be provided only by the RB. RA and RC should not provide attenuation. So if they should not provide attenuation, why are they included? Okay, that we will see again. Okay, let's go back to the actual description. The center circular section containing the resistive card RB can be rotated by 360 degree. So this statement is important. The RA and RC are fixed cards, whereas center card, that is RB, can be rotated by entire 360 degree with respect to the two fixed resistive cards. The induced current on the resistive card RA due to incident signal is dissipated as a heat. Sorry, this should not be RA, this should be RB. Here it should be RB. The induced current on the resistive card RB due to incident signal is dissipated as a heat, producing attenuation of the transmitted signal. Okay, so RA and RC are not producing any attenuation. RB will produce attenuation, and again similar to coaxial line attenuator, it will be dissipated as a heat. The TE10 mode in RCT is converted into TE11 in circular waveguide. Okay, so the purpose of the first and last, that is RA and RC, is to convert TE10 into a TE11 mode. Okay, because for TE11 mode we can provide easy attenuation as we desire. TE11 is not a dominant mode for a rectangular, but it is a circular dominant mode for circular waveguide, and that's why this conversion is necessary. So in short, RA and RC are not producing any attenuation. Their job is to convert TE10 mode into TE11. Why TE11? Because the center part is a circular waveguide. We have kept it as a circular waveguide because we want to rotate the dielectric slab. For rotation to be easier, we have kept it as a circular waveguide. And for circular waveguide, TE11 is a dominant mode. And to achieve TE11, you need transition from TE10 to TE11. Now, why we are entering as a TE10 mode? Because entering part is a rectangular waveguide which has to have TE10 as a dominant mode. Okay, you can also use a simple circular waveguide, but then it will become simple coaxial line type fixed attenuator. Okay, so let's see further. The resistive cards RA and RC kept perpendicular to the electric field of TE10. So this is if TE10 in this direction, these cards will be on the Z direction, that is like this. So that is different from our phase shifter. Okay, so they do not absorb the energy because they are in the direction of wave propagation. This is the direction of wave propagation. This is the direction of electric field. So waves are traveling in this direction, and these RA and RC are in the same direction. So they do not absorb the energy. But any component parallel to its plane will be readily absorbed. And this is a parallel to electric field, and it can be rotated, so it will absorb the energy. Hence in the TE mode, hence in the circular waveguide, TE11 mode is excited and amount of attenuation is applied by the resistive card or dielectric slab which is placed inside the circular waveguide, which is denoted as RB in this case. Okay, so this is how it is constructed. Now if the resistive card in the center section is kept an angle of theta relative to the E field, so as you can see in this diagram, this is RCT, this is CW, and this is CRT. Now as we are saying, if RB is kept at an angle of theta relative to the electric field direction of TE11 mode, so this is the theta which is shown over here, then the component E cos theta, which will be parallel to the card. So component E cos theta, as you can see here, is a parallel to the card. So this is our actual location of a card This is the actual location of a card. E cos theta will be parallel to the chord. E sin theta will be perpendicular to the original location of the chord. We are moving the card by theta degree. Initially it was like this as shown in this figure. Okay, initially this is the initial location of the card. Then we are moving it by the theta degree. When we move it by theta degree, e cos theta becomes parallel to the initial location and e sin theta becomes the perpendicular to the initial location. Okay, now since this is parallel location, it will not absorb energy. It will get absorbed while the component e sin theta is transmitted without attenuation. Okay, so this will be transmitted and this will be absorbed. This component finally comes out as a e sin square theta because it has to further go down to the CRT where it will be multiplied to be e sin square theta. Okay, so that is how attenuation is observed. And if you closely follow, and this is the big reason, because we see the phase shifting also. So we are moving, or we are getting output as a e sin square theta, which is different than the original input, which was only e. So sin theta means there is a phase change of certain amount of degree, and that is why this can act as a phase shifter also, but the arrangement have to be different to achieve the desired phase shift. So forget about phase shifting. Right now let's concentrate on attenuation. So the center part provides attenuation. These two parts are for conversion of TE10 to TE11 mode. Okay, so that is precision rotary type attenuator. So we have seen different types of attenuators like coaxial fixed attenuator, then movable vane type attenuator, then flap attenuator, and finally precision type variable attenuator. So 3 variable attenuators and 1 fixed attenuator we have seen. That's all for today. In the next session we will see the different types of ferrite devices which are used in the microwave circuit. Thank you.